Okay, so these examples ask that you find the limit as x approaches a graphically. And we see multiple graphs. They look pretty different. That one is like a parabola. That's like 1 over x that we saw before. That looks like tangent from the trigonometric functions. This looks like our first example. That was the weird one. So we all got familiar things, so we're not too worried about that answers. So the first one, let's do it. So we have this a right here. And before we actually do this problem, this function has nothing fishy or no holes and no weird asymptotes in there. So there's nothing wrong with it, I guess. So this one should be easy. And let's see if we follow along with our fingers. We get really, really close to A. Our fingers meet and we get really close to 5. So this one would be 5. For this one, as we approach A, we don't need to follow along our fingers with that side because A is over here. So we can follow along with our fingers. And if we go from the left side, we get really, really close to A, and we get really close to A on this side. Now we're getting really close, and our fingers are meeting, and they are very close to 1. So if we approach A, we get really close to it, from both the left and the right, we get really close to 1. This example says, okay, we have A here. Oh, there's an asymptote right at A. What's going to happen? From the left side, we're approaching really, really big. From the right side, we're getting really small. Small, I mean negative. We're getting really, really negative. And these are not going to meet. My fingers are not going to meet. So the function's going opposite direction to them. So the limit can't exist because they're approaching different values. So this does not exist. So this one, we have a hole. Interesting. But if I follow along the graph, if I get really, really close to A, I'm going to meet up soon. But we get really, really close to 2. Really close to 2. So the limit equals 2. And this one's the last one. It's kind of a doozy. But this is A. This is where the weird stuff happening. But we have to follow along the function right here, on the left and the right. So if we follow along, we're going to approach 2 different values. This one approaches 3 on the left side. This approaches 1 from the left side, so right side. And those are 2 different values. My fingers are not going to meet up. The limit does not exist. Okay, that's the problem that you were supposed to do. My videos aren't to make you 100% on everything. They're just for you to get the concept. And there's not a lot of math involved right now, but it just gets worse, you know? It's gonna get worse. But it's fine. It's not that bad. Okay, so now let's talk about we talked about limits graphically. We're still talking about limits. So I should have changed that. But we're now evaluating them and we're looking at them at analytical perspectives. So analytically, solving these limits. Okay, so for analytical reasons, limits, we need to know algebraic functions. And then we'll need to know trigonometric functions. Not transcendental, just trigonometric functions, algebraic functions. So now we're over here evaluating. Okay. So remember that one example where we had x plus 1 times x minus 2. This is a factor form of a rational function. But what we have here is a function, an algebraic function, and it's approaching some value too. Now if you've noticed, graphically, that if our function does not have any mess, like our parabola, quadratic, you'll say if we have a limit, and it's approaching this point right here, it actually equals our function value. So, what's the point of limits? Well, if we don't have that value, we can't just plug in our point. But if our function doesn't have any issues, we can plug in the point and the limit, and I'll just say this, the limit as x approaches a of our function actually equals our function value at that point. And you can see that if I trace my hands. But with this example, if you can visually look at this, we get something like this. And this is 2. And what we see here is that, we're approaching. Oh, but the function is undefined there. The function is undefined there if we plug in 2. And if you plug in 2 in here, the function is undefined. You get 0 over 0. And this is where people just give up. Like, I don't know how to get it without knowing the graphs. Well, visually, what is it? It's this value right here. This value right here. Because if I trace my hands, I get really, really close to 2. We get really close to L. So, how do we fix this problem? Well, the way we fix it is we say, hey, let's pretend this point did exist. And we didn't have that hole at all. So we just kind of filled it in. And now, if we plug in 2, we get L. But how do we do that without having the graph and having this thing only? And this is where we cancel out the problems. We're removing our issue. And if you see that there's a common factor on the top and bottom, and that they cancel out, this would equal the limit as x approaches 2 of x plus 1. And it's just x plus 1. Now you're removing a domain value. What you're removing is the ability to plug in 2 and get something undefined. Now if you plug in 2, you actually get a number. And the number we get is 3. And this is the way we kind of remove that hole and fill it in with something else. That's the easiest thing to get. is to cancel out what's causing the issue. Let's go over some limit properties first before we get a little bit more nasty with this. So, we have some limit properties that we need to get out of our way. And these are very neat. Well, kind of. If we have the limit as f of x approaches, as x approaches a, sorry, of f of x plus g of x, this is basically saying if we're taking a limit of two functions that are being added together. This equals the limit as x approaches of f of x plus the limit as x approaches a of g of x. Basically, we can separate the limit of each. Okay. We can do that with both positive and negative. We got another one. This one is for products. Now the product one also is neat. It's saying if we get multiplied by two functions, we can actually separate it by multiplication. Now the way you would prove these properties is by using the formal definition, which is kind of nasty, but it's not nasty, it's just kind of weird and confusing to look at. That's why I don't cover it right now. So you can multiply these. There's another one, it's for division. You can separate limits by division, provided that that one doesn't equal 0, that doesn't. But I won't. Okay. The last one is pretty cool. It's saying if you have a limit as x approaches a of a function raised to some power, what you can do is you can take the limit as x approaches a of that function and then raise it to that power. Now, I'm going to be honest. Do I mentally, visually use any of these rules in the future? No. But I use them. But I don't make them look like this. And I'll show you what that means. But you won't really use any of these, and you won't mathematically put them like this, but just showing you that it works. And if you know the pattern, you're not going to really use these. You're not going to physically do any of these. You just know it happens that way. So these are the rules that you know. Okay. So those are the rules. There's one rule that kind of makes these all nice. So, remember polynomials, studying them? This is a nasty one, but it doesn't have any holes, it doesn't have any asymptotes. It's always well defined. So that means if I have any point, A, B, C, or D, and I say, well, let's make a limit as x approaches any of these x, and you see that they always approach their function value. They always approach their function value. If I had axes, this one would approach, well, that would approach f of A, and that would approach f of B. They would always approach what their function gives out. And this means that we have another kind of property. It is the limit as x approaches A of a polynomial p of x. And it will always equal p of A. So we could just plug the value. We could just plug it in, and you'll get it. It's the one way I talked about this one as a quadratic, this polynomial. It's well defined. It's continuous. Has no asymptotes. Has no holes. If I take the limit as x approaches A, oh, what is it? It's right here. It approaches. Oh, that's f of A. It's the same thing. That's why this one works. Okay. It's been 16 minutes. And all I've done is just introduce the rules and everything. We haven't even done any of these limits yet. So let's do some limits. Let's do the limit as x approaches 2 of x squared plus 2x. Did I run out? What's that battery little thing? Okay. Okay. The flash made the battery low. I didn't even want to use flash, but whatever. So 2x plus 2. Oh. We can actually use the limit properties. And we can separate every function hey. If our limit is exposed to a constant, it's always C constant. If we approach any value from left and right of a constant, it'll always be that same value. That's why that works. But so I can separate all these, and then I could use I can use all my rules. All of my rules. I can say, well, that's a polynomial. I can just wait a second. I can separate. I can pull out my power, and then I can pull out my constants, and I'm doing this really fast. I can pull out my constants. I can do all that. It will work. That's another problem. You can pull out the constants. Pull out and multiply. Wait. Plug in 2 to the x. get 2 squared plus 2 times polygon 2 plus 2. Wait a second. What did we just do? We actually physically plugged it all in. What was the point of doing this? We have this property. What was the point of doing it? And that is why you don't really use these rules. Because from all these rules, you actually get that right. And this would be what? 4 plus 4 plus 2, which is 10. Huh? Kind of unnecessary. Could have just got that from the start. We could have just plugged in 2 because it was a polynomial. Okay. Now let's do a little bit more weird stuff. Let's do... Is that a polynomial? No. So we can't use that rule. Oh wait. We can separate these by division, the function. Ooh, I see. You can separate limits by division. Hey, is this a polynomial? Yes. Is this a polynomial? Yes. Just plug it in. Oh, what do we get? That's the 10. That's the 9. Wait a second. Was this necessary? We could have literally just plugged it in and got it again. Kind of questioning these rules now. Why do we need them? We could just plug in their values. Why would we need these rules? These rules are needed to prove this rule and all the other rules. So we can get to the point where we can do some weird stuff. So, at this point, no matter what function is, if it was a square root function, if it was a square root of x squared plus 2x, hey, that's not a polynomial. But remember this n to power rule, if we have a function to some power. Wait a second. Let's just do the 1/2 power. We can raise the entire limit to the 1/2 power. Wait, we can just plug it in because it's a polynomial. What is that going to be? 4, that's 8, that's 13 to the 1/2 power. Wait a second, that's like as if we plugged that in over here. We could have just plugged that in. We could just put 2 in there and it would give us the same answer. And these rules kind of show us that we can just plug any number in and get the limit out. So all these rules prove this one rule and this one rule. With all these rules, all show us that we can just plug in our values. We can just plug in our values. It's been 24 minutes, and we haven't gotten anywhere. These are all the rules, and we just put them on some functions, and we're like, wait, this rule, we just figured that out, knowing all these rules. That is true. Wait. These rules. A polynomial of a polynomial, polynomial for any nth power. We can combine all these rules and we'll actually create any algebraic function possible. And all you're doing is just plugging in the point. So why use all these rules when you could just plug it in? You're using the rules You're proving that, hey, I know these rules work. And because these rules work, you can just plug it in. Because what you're doing is that you're proving that you can plug in your point. There is no reason. All these rules do is you can prove that you can plug in the number in. That is all. My memory might want to go away. But here's when things get a little fishy. Is when you get undefined answers. If you just plug it in. We're going to deal with those. So I feel like it's been a 25-minute waste. But it was just to show that, hey, wait a minute, there's so much rules to them, but all they prove to you is that you can just plug in a point. The number in. But if it doesn't work out, if there is some error in your math calculator, then there's an issue. And that is why we're going to take all that and cover it next time. The last one property that I do want to share with you before I end this video